agricultural science that focuses on the study of crop production and soil management to optimize agricultural practices. It encompasses various aspects of plant science, soil science, and meteorology to enhance the efficiency and sustainability of crop production. The primary goal of agronomy is to maximize the yield and quality of crops while minimizing the negative impacts on the environment. The scope of agronomy includes 1. Crop production. Agronomists study the growth, development, and management of crops. This involves selecting suitable varieties of crops, determining the best planting and harvesting times, and developing strategies to optimize crop yields. 2. Soil management. Agronomy involves understanding soil properties, fertility, and structure. Agronomists work to improve soil health through practices such as nutrient management, soil conservation, and erosion control. 3. Crop protection. Agronomists are involved in the study of pests, diseases, and weeds that can affect crop growth. They develop strategies for integrated pest management, which may include the use of pesticides, biological control, and other methods to protect crops. 4. Agroecology. Agronomy considers the ecological aspects of agriculture, aiming to achieve a balance between crop production and environmental sustainability. This includes promoting practices that minimize the impact of agriculture on ecosystems. 5. Crop physiology. Understanding the physiological processes of plants is crucial in agronomy. This includes studying how crops respond to environmental factors such as light, temperature, and water, and how they absorb nutrients from the soil. 6. Precision agriculture. With advancements in technology, agronomy has embraced precision agriculture, which involves using technologies such as GPS, sensors, and data analytics to optimize field-level management with regard to crop farming. 7. Climate and weather impacts. Agronomy takes into account climatic factors and weather patterns that can affect crop production. This includes developing strategies to adapt to changing climate conditions and mitigate the impact of extreme weather events. 8. Sustainable agriculture. As global concerns about environmental sustainability and resource conservation grow, agronomy plays a key role in promoting sustainable agricultural practices. This involves minimizing the use of inputs, reducing environmental impacts, and promoting practices that ensure the long-term viability of agriculture. In summary, agronomy is a multidisciplinary field that integrates knowledge from various scientific disciplines to enhance agricultural productivity, sustainability, and resilience. Agronomists work to develop and implement practices that contribute to efficient and responsible crop production. National and international agricultural research institutes of LNDIA. India has several national and international agricultural research institutes that play a crucial role in advancing agricultural science, technology, and practices. These institutions focus on research and development to address challenges in crop production, soil management, pest control, and other aspects of agriculture. Here are some prominent national and international agricultural research institutes in India. National Agricultural Research Institutes in India. 1. Indian Council of Agricultural Research, ICAR, is the apex body for coordinating, guiding, and managing research and education in agriculture in India. It oversees numerous agricultural research institutes and universities across the country. 2. Indian Agricultural Research Institute, IAI, located in New Delhi. IAI is one of the premier institutes under ICAR. It focuses on research in various aspects of agriculture, including crop improvement, plant pathology, soil science, and agricultural engineering. 3. National Institute of Agricultural Economics and Policy Research, NIAP, is dedicated to research on agricultural economics and policy issues. It provides valuable insights into the economic aspects of agriculture and rural development. 4. Central Soil Salinity Research Institute, CSSI, based in Karnal, Haryana. CSSI is involved in research related to soil salinity and water management. It works towards developing technologies to reclaim salt-affected soils. 5. Central Rice Research Institute, CRI, located in Cuttack, Odisha. CRI is focused on rice research. It plays a crucial role in developing improved varieties of rice, pest management strategies, and sustainable rice cultivation practices. 6. Central Potato Research Institute, CPI, headquartered in Shimla, Himachal Pradesh, is dedicated to potato research. It works on developing improved potato varieties, disease management, and post-harvest technologies. International Agricultural Research Institutes with collaboration in India. 1. International Crops Research Institute for the Semi-Arid Tropics, ICRISAT, is headquartered in Hyderabad, Telangana. It focuses on improving agricultural productivity in the semi-arid tropics, with an emphasis on crops such as sorghum, millet, chickpea, pigeon pea, and groundnut. 2. International Rice Research Institute, III, although based in the Philippines, III collaborates extensively with Indian agricultural research institutions. It is a global center for rice research, working on the development of improved rice varieties and sustainable rice production practices. 3. International Maize and Wheat Improvement Center, CIMMYT collaborates with Indian institutions to improve maize and wheat varieties. It plays a crucial role in global food security through research on these staple crops. Collaborations with international agricultural research institutes help India access global expertise, share research findings, and adopt best practices for sustainable agricultural development. These institutions contribute significantly to the progress and innovation in the agricultural sector in India. Agroclimatic zones of LNDIA and Bihar. India exhibits a diverse range of agroclimatic zones due to variations in topography, climate, and soil types. Each agroclimatic zone has its own set of crops that are well suited to the local conditions. Bihar, a state in eastern India, also experiences diverse agroclimatic conditions. Here is an overview of the agroclimatic zones in India and specific details about Bihar. Agroclimatic zones of India. 1. Western Himalayan region includes Jammu and Kashmir, Himachal Pradesh, and Uttarakhand. Crops like apples, cherries, and temperate vegetables are grown here. 2. Eastern Himalayan region covers Arunachal Pradesh, Nagaland, Manipur, Mizoram, Tripura, Meghalaya, and the hilly areas of Assam. It is suitable for crops like citrus fruits, tea, and spices. 3. Lower Gangetic Plains region encompasses the plains of West Bengal and the eastern parts of Bihar. Rice, jute, sugarcane, and pulses are some of the major crops. 4. Middle Gangetic Plains region spreads across the central parts of Bihar and Uttar Pradesh. Major crops include rice, wheat, sugarcane, and oilseeds. 5. Upper Gangetic Plains region includes the western parts of Uttar Pradesh and Haryana. Wheat, barley, sugarcane, and oilseeds are common crops. 6. Transgangetic Plains region spreads over Punjab, Haryana, and parts of Uttar Pradesh. Wheat, rice, sugarcane, and cotton are important crops. 7. Eastern Plateau and Hills region covers Chhattisgarh, Jharkhand, and the eastern parts of Madhya Pradesh and Odisha. Crops include rice, oilseeds, pulses, and coarse grains. 8. Central Plateau and Hills region encompasses parts of Madhya Pradesh, Maharashtra, and Chhattisgarh. Crops like millets, pulses, and oilseeds are grown. 9. Western Plateau and Hills region covers parts of Gujarat, Rajasthan, and Madhya Pradesh. Millets, pulses, oilseeds, and cotton are common crops. 10. Southern Plateau and Hills region encompasses parts of Karnataka, Andhra Pradesh, and Tamil Nadu. Major crops include millets, pulses, oilseeds, and cotton. 11. Coastal Plains region includes the coastal areas of Gujarat, Maharashtra, Goa, Karnataka, Kerala, Tamil Nadu, Andhra Pradesh, Odisha, and West Bengal. Rice, coconut, spices, and fruits are grown. 12. Western Dry region spreads over Rajasthan, Gujarat, and parts of Haryana and Punjab. Millets, pulses, oilseeds, and cotton are common. 13. Southern Dry region encompasses parts of Karnataka, Andhra Pradesh, and Tamil Nadu. Millets, pulses, and oilseeds are important crops. 14. Islands region includes the Andaman and Nicobar Islands, Lakshadweep, and the coastal areas of Tamil Nadu and Kerala. Coconut, rubber, and tropical fruits are grown. Agroclimatic zones of Bihar. Bihar, being a diverse state, experiences multiple agroclimatic zones. Some of the key zones include 1. Northwest alluvial plains, suitable for rice, wheat, sugarcane, and oilseeds. 2. Northeast alluvial plains, dominated by rice cultivation, along with wheat, pulses, and oilseeds. 3. Southwest alluvial plains, suitable for rice, maize, sugarcane, and oilseeds. 4. Southeast alluvial plains, primarily for rice, along with pulses, oilseeds, and sugarcane. 5. Hilly region, focused on horticulture and floriculture, including fruits like mango and lychee. Understanding the agroclimatic zones is crucial for farmers and policymakers to make informed decisions regarding crop selection, agricultural practices, and resource management. It helps optimize agricultural productivity and sustainability based on the local climate and soil conditions. Weather and climate. Weather and climate. Weather. Definition. Weather refers to the atmospheric conditions in a specific place at a particular time. It includes short-term variations in temperature, humidity, precipitation, wind speed, and atmospheric pressure. Timescale. Weather conditions change frequently and are observed over a short period, typically hours to a few days. Factors influencing weather: solar radiation, atmospheric pressure, temperature, humidity, wind patterns, and geographical features play a significant role in determining daily weather patterns. Climate. Definition. Climate represents the long-term patterns and averages of weather conditions in a particular region over an extended period, usually 30 years or more. Timescale. Climate provides a broader perspective and is characterized by the average weather conditions, including temperature, precipitation, and other atmospheric elements, over an extended period. Factors influencing climate: latitude, altitude, proximity to water bodies, ocean currents, and geographical features contribute to the climate of a region. Key differences. 1. Timescale. Weather is short-term, focusing on immediate atmospheric conditions. Climate is long-term, representing the average weather patterns over an extended period. 2. Variability. Weather can change rapidly, sometimes from day to day or even within hours. Climate is more stable and reflects the general atmospheric conditions characteristic of a particular region. 3. Scope. Weather is local and specific to a particular place at a given time. Climate encompasses larger geographical areas and provides a broader understanding of regional weather patterns. 4. Measurement. Weather is measured using various instruments such as thermometers, barometers, anemometers, and rain gauges. Climate is assessed through long-term data collection, statistical analysis, and the study of patterns over decades. 5. Examples. Weather includes daily conditions like sunny, rainy, windy, or snowy. Climate describes the characteristic weather of a region, such as a tropical climate with high temperatures and rainfall, or a polar climate with cold temperatures. Understanding both weather and climate is essential for various purposes, including agriculture, urban planning, disaster preparedness, and environmental studies. Weather influences daily activities, while climate shapes the overall ecosystem and lifestyle of a region over an extended period. Microclimate. Microclimate. Microclimate refers to the localized atmospheric conditions within a small and specific area that may differ from the surrounding or regional climate. These variations in temperature, humidity, wind speed, and other atmospheric factors are influenced by the characteristics of the local environment. Microclimates can exist within larger climate zones and can be found in various natural and human-made settings. Here are some key features and examples of microclimates. 1. Factors influencing microclimate. Topography. Features such as mountains, valleys, and slopes can create variations in temperature and precipitation within a small area. Vegetation. The presence of vegetation, such as forests or urban green spaces, can impact temperature, humidity, and wind patterns. Water bodies. Proximity to lakes, rivers, or oceans can influence local temperatures and humidity levels. Urbanization. Urban areas may have their own microclimates due to factors like heat retention in buildings, pavement, and the urban heat island effect. 2. Characteristics of microclimates. Temperature. Microclimates can have temperature variations compared to the surrounding areas. For example, urban areas may experience higher temperatures than nearby rural areas. Humidity. Vegetated areas or bodies of water can contribute to increased humidity in a microclimate. Wind. Buildings, hills, or other structures can create wind patterns unique to a specific location. Precipitation. Some areas may receive more or less rainfall than the surrounding region due to local factors. 3. Examples of microclimates. Urban heat island. Cities tend to have higher temperatures than their rural surroundings due to human activities, dark surfaces, and reduced green spaces. Mountain valleys. Valleys between mountains can create temperature inversions, trapping cold air and leading to temperature differences compared to higher elevations. Forest clearings. Open spaces within forests may experience different temperature and humidity levels than the dense forest areas. Coastal microclimates. Coastal areas may have milder temperatures compared to inland regions due to the moderating influence of the ocean. 4. Importance. Agriculture. Understanding microclimates is crucial for optimizing crop selection and cultivation practices. Urban planning. Consideration of microclimates is essential for designing sustainable and comfortable urban environments. Ecology. Microclimates play a role in shaping local ecosystems and biodiversity. Overall, the study of microclimates provides insights into the nuances of climate variations at a smaller scale, contributing to more informed decision-making in various fields. Weather elements. Weather elements refer to the various components or parameters of the atmosphere that are measured to describe and understand the current atmospheric conditions. These elements help meteorologists and scientists analyze and predict weather patterns. Here are the key weather elements. 1. Temperature. Definition. The measure of the warmth or coldness of the air. Measurement unit. Degrees Celsius, degree C, or Fahrenheit, degree F. 2. Humidity. Definition. The amount of moisture or water vapor present in the air. Measurement unit. Percentage, % symbol. 3. Precipitation. Definition. Any form of water, liquid or solid, falling from the atmosphere and reaching the ground. It includes rain, snow, sleet, and hail. Measurement unit. Usually measured in millimeters, millimeter, or inches. 4. Atmospheric pressure. Definition. The force exerted by the air molecules in the atmosphere. It decreases with altitude. Measurement unit. Hectopascals, HPA, or millibars, MB. 5. Wind speed. Definition. The rate at which air moves horizontally past a given point. Measurement unit. Generally measured in kilometers per hour, kilometer, h, or meters per second, ms. 6. Wind direction. Definition. The direction from which the wind is blowing, expressed in compass points, example, north, south, east, west. Measurement unit. Degrees in meteorological notation. 7. Cloud cover. Definition. The fraction or percentage of the sky covered by clouds. Measurement unit. Percentage, % symbol. 8. Visibility. Definition. The distance at which objects can be clearly seen in the atmosphere. Measurement unit. Meters, m, or miles, mi. 9. Dew point. Definition. The temperature at which air becomes saturated with moisture and dew forms. It indicates the humidity level. Measurement unit. Degrees Celsius, degree C, or Fahrenheit, degree F. 10. Sunshine duration. Definition. The total time during which the sun is visible or the sky is not completely overcast. Measurement unit. Hours or minutes. These weather elements are measured using various instruments, such as thermometers, hygrometers, barometers, anemometers, and rain gauges. Collectively, the information gathered from these elements helps create a comprehensive picture of the current weather conditions and aids in weather forecasting. Advanced technologies, satellite observations, and weather stations contribute to accurate and timely data collection for analysis and prediction. Formation and classification of clouds. Clouds are formed when moist air rises and cools, causing water vapor to condense into tiny water droplets or ice crystals. The process of cloud formation involves several key factors, including temperature, humidity, and air currents. Clouds are classified based on their appearance, altitude, and the processes that lead to their formation. The World Meteorological Organization, WMO, has established an international cloud atlas that provides a standardized classification system for clouds. Formation of clouds. 1. Warming of air. Air near the Earth's surface is warmed by the sun, causing it to rise. As air rises, it expands and cools. 2. Saturation point. As the rising air cools, it may reach a point where it becomes saturated with moisture. This is called the dew point, and it is the temperature at which air becomes fully saturated and can no longer hold all its water vapor. 3. Condensation. When the air reaches its dew point, water vapor begins to condense into tiny water droplets or ice crystals around microscopic particles known as condensation nuclei. These particles can include dust, salt, or other airborne particles. 4. Cloud formation. The accumulated water droplets or ice crystals form clouds. The size and type of cloud depend on factors such as temperature, humidity, and the presence of other atmospheric particles. Classification of clouds. Clouds are classified into several types based on their appearance and altitude. The primary cloud types are divided into 4 main cloud genera, each with various species and varieties. 1. High-level clouds. Above 20,000 feet, or 6,000 meters cirrus, CI wispy, feathery clouds often indicating fair weather. Cirrostratus, CS thin ice crystal clouds covering the sky, often producing halos around the sun or moon. Cirrocumulus, CC small, white patches of clouds often arranged in rows at high altitudes. 2. Mid-level clouds, 6,500 to 20,000 feet, or 2,000 to 6,000 meters altostratus, as grey or blue-grey clouds that usually cover the entire sky, often preceding storms with continuous rain or snow. Altocumulus, AC white or grey clouds, usually forming a layer, often seen before a storm with continuous rain or snow. 3. Low-level clouds, up to 6,500 feet, or 2,000 meters stratus, ST grey clouds covering the sky like a blanket, often bringing drizzle or light rain. Stratocumulus, SC low, lumpy clouds covering the sky, often appearing darker than regular cumulus clouds. 4. Clouds with vertical development. Cumulus, CU white, fluffy clouds with a flat base, often indicating fair weather. Cumulonimbus, CB towering clouds with an anvil-shaped top, associated with thunderstorms, heavy rain, and severe weather. These cloud classifications provide meteorologists with valuable information about the atmospheric conditions and help in predicting weather patterns. The combination of cloud types and their characteristics is indicative of the current and future weather conditions in a particular region. Basics of weather forecasting. Weather forecasting is the process of predicting the state of the atmosphere at a specific location and time in the future. It involves the use of scientific principles, data analysis, and advanced technologies to provide accurate and timely information about upcoming weather conditions. Here are the basics of weather forecasting. 1. Data collection. Observation stations, meteorological stations, weather balloons, and satellites collect data on temperature, humidity, atmospheric pressure, wind speed and direction, and other relevant parameters. Radar and satellite imagery. Remote sensing technologies provide real-time images of cloud cover, precipitation, and atmospheric circulation patterns. 2. Numerical weather prediction. NWP computer models. Numerical weather prediction involves the use of computer models that simulate the behavior of the atmosphere based on the observed data. These models use mathematical equations to represent the physical processes of the atmosphere. Data assimilation. The observed data is assimilated into the models to improve accuracy and reliability. 3. Forecasting techniques. Persistence forecasting assumes that current weather conditions will continue without significant change. This method is often used for short-term forecasts. Climatology relies on historical weather data for a specific location to predict average conditions for a given time of year. It is useful for long-term forecasts. Analog forecasting compares current weather patterns to past patterns with similar characteristics to make predictions. 4. Short-term forecasting, nowcasting, provides short-term forecasts up to a few hours based on current observations, satellite imagery, and radar data. It is useful for immediate weather concerns. Weather radar helps predict the movement and intensity of precipitation, including storms. 5. Medium range and long range forecasting, climate models. For forecasting beyond a week, climate models are used to predict broad patterns based on historical climate data and trends. Teleconnections, examining relationships between large-scale atmospheric and oceanic patterns to make predictions about general weather patterns on a regional or global scale. 6. Verification and updates. Forecasts are continuously verified against actual observed weather conditions to assess accuracy. Meteorologists regularly update forecasts based on the latest data and model outputs. 7. Communication. Meteorologists communicate forecasts to the public through various channels, including television, radio, websites, and mobile apps. Forecasts often include information about temperature, precipitation, wind speed, and other relevant factors. 8. Challenges and uncertainties. Weather forecasting is inherently uncertain due to the chaotic nature of the atmosphere. Forecasts become less accurate as the prediction period extends into the future. Advancements in technology, such as improved satellite systems, computer models, and data assimilation techniques, have significantly enhanced the accuracy of weather forecasting. Despite challenges, accurate and timely weather forecasts are crucial for various sectors, including agriculture, transportation, emergency management, and everyday planning. Dry land agriculture. Dryland agriculture refers to agricultural practices carried out in regions where water availability is limited, and there is a significant dependence on rainfall for crop cultivation. These areas, often characterized by arid or semi-arid climates, face challenges such as low and erratic precipitation, high evaporation rates, and poor soil fertility. Dryland agriculture requires specific strategies to conserve water, enhance soil productivity, and adapt to the challenging environmental conditions. Here are key aspects of dryland agriculture. 1. Crop selection. Drought-tolerant crops. Choose crops that are well adapted to arid conditions and have the ability to withstand water scarcity. Examples include millets, sorghum, pearl millet, and certain varieties of pulses. 2. Water conservation. Rainwater harvesting. Collect and store rainwater for agricultural use through techniques like building check dams, contour bunding, and constructing small reservoirs. Water-efficient irrigation. Utilize efficient irrigation methods such as drip irrigation and rainwater harvesting pits to optimize water use. 3. Soil management. Conservation tillage. Adopt minimum tillage or no-till practices to reduce soil erosion and retain soil moisture. Organic matter addition. Incorporate organic materials into the soil to improve its structure, water holding capacity, and nutrient content. 4. Crop rotation and diversification. Diversified cropping systems. Implement crop rotation and diversification to reduce the risk associated with a single crop failure and improve overall productivity. Legumes. Include leguminous crops in the rotation as they contribute to nitrogen fixation, enhancing soil fertility. 5. Agroforestry. Tree planting. Integrate trees with crops to provide shade, reduce evaporation, and improve microclimatic conditions. Agroforestry systems can contribute to improved soil fertility and water retention. 6. Improved seeds and varieties. Drought-resistant varieties. Use crop varieties that are specifically bred or adapted to withstand water scarcity and harsh climatic conditions. Short-duration crops. Opt for crops with shorter growth cycles that align with the available water resources. 7. Agronomic practices. Mulching. Apply mulch on the soil surface to reduce evaporation, control weeds, and conserve soil moisture. Contour farming. Implement contour plowing to minimize soil erosion and enhance water infiltration. 8. Community-based management. Water user groups. Establish community-based organizations to manage water resources collectively and promote sustainable water use practices. 9. Technology adoption. Satellite technology. Utilize remote sensing and satellite technology for monitoring vegetation health, assessing water availability, and making informed decisions on agricultural management. 10. Government support and policies. Subsidies. Implement government policies that provide subsidies for adopting water-efficient technologies and practices. Extension services. Strengthen agricultural extension services to educate farmers about best practices for dryland agriculture. Dryland agriculture is crucial for food security in many parts of the world, particularly in arid and semi-arid regions. Implementing sustainable and water-efficient practices is essential for enhancing agricultural productivity while preserving the fragile ecosystems of these regions. Area, production and productivity of major crops in India and Bihar. As of my last knowledge update in January 2022, I can provide you with general information on the area, production, and productivity of major crops in India and Bihar. However, please note that the data may have changed, and it is advisable to refer to the latest reports from official agricultural departments or organizations for the most recent information. India. 1. Rice, area, 2019 to 20 approximately 43.35 million hectares production, 2019 to 20 about 118.87 million metric tons productivity, 2019 to 20 around 2.75 tons per hectare 2. Wheat, area, 2019 to 20 approximately 30.74 million hectares production, 2019 to 20 about 107.59 million metric tons productivity, 2019 to 20 around 3.50 tons per hectare 3. Oilseeds including groundnut, soybean, mustard, and sunflower area, 2019 to 20 approximately 26.54 million hectares production, the 2019 to 20 about 31.42 million metric tons productivity, the 2019 to 20 around 1.18 tons per hectare 4. Sugarcane, area, 2019 to 20 approximately 5.13 million hectares production, 2019 to 20 about 353.85 million metric tons productivity, 2019 to 20 around 68.96 tons per hectare 5. Cotton, area, 2019 to 20 approximately 12.71 million hectares production, 2019 to 20 about 25.68 million bales, of 170 kilograms each, productivity the 2019 to 20 around 464 kilograms per hectare. Bihar. 1. Rice, area, 2019 to 20 approximately 5.34 million hectares production, 2019 to 20 about 11.15 million metric tons productivity, 2019 to 20 around 2.09 tons per hectare 2. Wheat, area, 2019 to 20 approximately 2.72 million hectares production, 2019 to 20 about 6.42 million metric tons productivity, 2019 to 20 around 2.36 tons per hectare 3. Oilseeds including groundnut, soybean, mustard, and sunflower area, 2019 to 20 approximately 1.14 million hectares production, the 2019 to 20 about 0.87 million metric tons productivity, the 2019 to 20 around 0.76 tons per hectare 4. Sugarcane, area, 2019 to 20 approximately 0.31 million hectares production, 2019 to 20 about 2.44 million metric tons productivity, 2019 to 20 around 79.34 tons per hectare 5. Cotton, area, 2019 to 20 approximately 0.08 million hectares production, 2019 to 20 about 0.08 million bales, of 170 kilograms each, productivity the 2019 to 20 around 191 kilograms per hectare. These figures are indicative and may vary from year to year based on factors such as weather conditions, agricultural practices, and government policies. It's essential to refer to the latest reports from reliable agricultural sources for the most up-to-date information. Tillage, crop stand establishment. It appears there might be some typos in your question, but I'll address what I believe you're asking about: tillage and crop stand establishment. 1. Tillage. Definition. Tillage refers to the mechanical preparation of the soil to create a suitable seedbed for planting. It involves activities such as plowing, harrowing, and cultivating to break up soil clods, control weeds, and incorporate organic matter. Objectives. Tillage has several objectives, including seedbed preparation, weed control, soil aeration, and incorporation of crop residues. It can also help manage soil moisture and improve nutrient availability. Types of tillage. Conventional tillage involves turning over the soil with plows or other implements, often inverting the soil layers. This can lead to soil erosion, but may be necessary for certain crops. Reduced tillage involves minimal disturbance of the soil, leaving a protective cover of crop residues. It helps reduce soil erosion and improves water retention. No-till involves planting crops directly into untilled soil. This method preserves soil structure, reduces erosion, and enhances water conservation. 2. Crop stand establishment. Definition. Crop stand establishment refers to the successful germination and emergence of crops, resulting in a uniform and desirable plant population in the field. Factors affecting crop stand. Seed quality. The use of high-quality seeds with good germination rates is crucial for uniform stand establishment. Seedbed preparation. Properly prepared seedbeds with suitable soil structure and moisture levels contribute to successful germination. Planting depth. Planting seeds at the correct depth ensures proper access to moisture and nutrients for germination. Planting density. The appropriate spacing between seeds or seedlings is important for achieving the desired plant population. Soil moisture. Adequate soil moisture is essential for germination and early seedling growth. Temperature. Suitable temperature ranges promote optimal germination and early growth. Methods of crop stand establishment. Direct seeding. Planting seeds directly into the field without transplanting. Common in crops like rice, wheat, and some pulses. Transplanting. Growing seedlings in nurseries and then transplanting them into the main field. Common for crops like tomatoes, peppers, and cabbage. Drilling. Using equipment like seed drills to place seeds at precise intervals and depths. Broadcasting. Spreading seeds evenly over the soil surface. Crop stand assessment. Plant counts. Regularly monitoring the number of plants per unit area to assess the success of stand establishment. Emergence uniformity. Observing the uniformity of seedling emergence across the field. Early vigor. Assessing the initial growth and health of seedlings shortly after emergence. Both tillage and crop stand establishment practices play vital roles in successful agriculture, influencing factors such as soil health, water conservation, and overall crop productivity. Sustainable and well-managed practices are essential for optimizing these processes. Planting geometry and its effect on growth and yields of cropping systems. Planting geometry, also known as crop spacing or arrangement, refers to the pattern and spacing at which crops are planted in a field. The choice of planting geometry can significantly influence the growth, development, and yields of cropping systems. The impact is often species-specific, and different crops may respond differently to various planting patterns. Here are some key aspects of planting geometry and its effects on cropping systems. 1. Plant population density. Effect: plant population density, determined by the spacing between individual plants, affects competition for resources such as light, nutrients, and water. Optimization. The goal is to achieve an optimal plant population density that maximizes yield without leading to excessive competition and stress among plants. 2. Row spacing. Effect: the distance between rows influences the amount of sunlight reaching the plants, as well as air circulation and disease management. Wide versus narrow rows. In some crops, narrow rows may enhance light interception and increase yield, while wider rows can facilitate better mechanical cultivation and reduce competition between plants. 3. Inter-row spacing. Effect: the spacing between individual plants within a row impacts plant growth, development, and yield. Thin versus thick planting. Thicker planting within rows may lead to competition for resources but can also optimize canopy cover, while thinner planting may reduce competition but increase the risk of weed growth. 4. Plant arrangement. Effect: the arrangement of plants, such as single rows, double rows, or square planting patterns, can influence light interception, nutrient utilization, and water efficiency. Companion planting. Some cropping systems involve planting different crops together to take advantage of complementary growth patterns and resource use. 5. Canopy architecture. Effect: planting geometry influences the structure of the crop canopy, which in turn affects light penetration and distribution within the crop. Canopy closure. A well-managed planting geometry can promote early canopy closure, maximizing light interception and photosynthesis. 6. Water use efficiency. Effect: proper planting geometry can enhance water use efficiency by optimizing the distribution of water to individual plants and reducing competition for water resources. Drip irrigation. In some cases, specific planting patterns are designed to complement drip irrigation systems, improving water delivery to each plant. 7. Nutrient uptake and soil fertility. Effect: planting geometry influences nutrient uptake efficiency and can impact soil fertility. Competition and cooperation. Proper spacing can balance the competition and cooperation among neighboring plants, ensuring efficient nutrient utilization. 8. Harvesting operations. Effect: the planting geometry can affect harvesting operations and the ease of mechanical harvesting, especially in row crops. Mechanical harvesting. Row spacing and plant arrangement may be adjusted to facilitate the use of mechanical harvesting equipment. 9. Pest and disease management. Effect: planting geometry can influence the microclimate within the crop canopy, affecting pest and disease prevalence. Air circulation. Proper spacing can enhance air circulation, reducing humidity and minimizing conditions favorable for certain diseases. 10. Biomass production. Effect: planting geometry influences the overall biomass production of the cropping system, impacting total crop yield. Optimizing resources. Proper spacing ensures efficient resource use, leading to optimal biomass accumulation and yield. It's important to note that the ideal planting geometry varies based on the specific crop, local climate, soil conditions, and the overall cropping system. Farmers and researchers often conduct experiments to determine the most suitable planting patterns for a particular set of conditions. Adjusting planting geometry can be a valuable tool for optimizing crop performance and increasing overall productivity in diverse cropping systems. Harvesting. Harvesting is a crucial stage in the agricultural process where mature crops are gathered from the field for further processing or consumption. The timing and methods of harvesting vary depending on the type of crop, its intended use, and local conditions. Here are key aspects of the harvesting process. 1. Timing of harvest. Crop maturity. Harvesting is typically done when crops reach their optimal stage of maturity. The timing varies among different crops and is influenced by factors such as growth cycle, weather conditions, and intended use, example, fresh consumption or processing. 2. Harvesting methods. Manual harvesting involves handpicking or using hand tools such as knives or sickles. It is commonly employed for fruits, vegetables, and certain grains. Mechanical harvesting utilizes machinery such as combine harvesters, reapers, or harvesters to automate the process. This method is often used for large-scale cultivation of grains like wheat, rice, and corn. 3. Crop-specific harvesting techniques. Fruits and vegetables. These are often handpicked to avoid damage and ensure that only ripe produce is harvested. Specialized tools or machinery may be used for specific crops. Grains. Mechanical combines are commonly used to cut, thresh, and clean grains in a single operation. The harvested grain is then collected for further processing or storage. Root crops. Root crops like potatoes and carrots are mechanically harvested using equipment that lifts the crops from the soil. 4. Post-harvest handling. Transportation. Harvested crops are transported from the field to processing facilities, markets, or storage facilities. Proper handling is essential to prevent damage and maintain quality. Storage. Some crops are stored for extended periods, requiring appropriate storage conditions to prevent spoilage. This may involve temperature and humidity control. Processing. Certain crops undergo additional processing after harvesting. For example, fruits may be sorted, washed, and packaged before reaching the market. 5. Harvesting for different purposes. Fresh market. Crops like fruits, vegetables, and herbs are often harvested for immediate consumption in their fresh form. Quality and appearance are critical in this context. Processing. Crops like grains, oilseeds, and sugar beets are harvested for processing into various products such as flour, oil, and sugar. Forage. Crops like hay and silage are harvested for use as animal feed. 6. Environmental considerations. Sustainability. Sustainable harvesting practices consider environmental impacts, such as minimizing soil disturbance, preserving biodiversity, and reducing energy consumption. Residue management. Proper residue management after harvesting can impact soil health, erosion control, and subsequent crop rotations. 7. Regulations and standards. Quality standards. Many countries have established quality standards for harvested crops to ensure food safety, nutritional quality, and fair trade practices. Harvesting permits and restrictions. Some crops may have specific regulations regarding harvesting permits, seasonal restrictions, or conservation measures. Efficient and timely harvesting is crucial for maximizing crop yields and ensuring the quality of agricultural products. Modern agriculture often integrates technology and precision farming practices to optimize the harvesting process. Additionally, post-harvest activities play a significant role in maintaining the quality and value of harvested crops throughout the supply chain. Classification of crops.